Good afternoon, everyone. Our today's speaker is Aritra Bakshi, a third year, sixth semester student of Presidency University. He will be presenting on the topic particle swarm optimization, gravitational wave astronomy. Over to you, Aritra.
Good afternoon, everyone. I am Aritra Bakshi of UG3 semester 6, and I will be talking about the topic of today's talk particle swarm optimization in gravitational wave astronomy, which I did as a part of my summer internship project under Professor Rajesh Kumar Nayak. The talk's outline will cover the theoretical background behind gravitational wave detection and how we can simulate a sharp signal, and we will see how different types of template work with each other. We will see how the injection and recovery of different parameters like mass and spin works and how particles optimization comes into play. We will see how the results go with the inclusion of PSO, and then going onward to the theory. We know gravitational waves are like ripples in space-time that are generated by massive objects or compact binaries like binary black holes or binary neutron stars, or even a neutron star and black hole when they spiral and continue to merge with each other. And when they merge or when they orbit around each other, the orbit shrinks, and due to the change in their frequency and amplitude which increase, a chirp like waveform is produced, which we detect as strain in the time domain ht, and then we transform it into the frequency domain using Fourier transforms, and we see a set of formulas which, without further going into detailed theory and mathematics, let us consider a detector with its two arms and a gravitational wave event occurring at this chi location here. This detector now is going to detect the gravitational wave emitted from this event. Now, to know its location in sky, we use something similar to the longitude and latitude. Here they are right extension with symbol alpha RA and declination DEC denoted by delta. What are these? Assume um, this is said this is the earth, and assume this to be the celestial equator with the vernal and autumnal equinox. The RA, this one, goes along this line like this here, starting from 0, 1, 2, 3, 4, and 12, and here 12, and then comes the 24. So this is the right ascension, and now in the declination, this one here goes from 0 to plus 90 and minus 90, this and this. So now we have the coordinates of the event alpha comma delta. Now from this chi position, the gravitational wave will get emitted and detected here as strain ht. Here this ht is nothing but the change in length delta L by the length L. This L is the length of the arms in the detector, this and this. Now as the wave comes, its quadruple moment affects the space. Say initially it was a circle with both arms of equal length. As the wave hits it, the change occurs, and after some time it changes into this elliptical shape with the y-axis getting stretched and the x getting compressed. Then again it becomes a circle, after which it forms this ellipse. Now y is compressed here and x gets extended. This is called the plus polarization of H plus here, and we have another polarization Hx here. Here the axis gets tilted at a 45-degree angle like this and this. Now along with these polarizations we have corresponding antenna patterns f plus and f cross or fx, as you can see. These functions of the sky map alpha delta along with the polarization angle form the sky antenna patterns, that these are constant for detectors, and with these we get the strain in the time domain using the formula ht equals to f plus times h plus f cross times h cross, and we use this strain in the frequency domain like this here. Here this is the amplitude, the chirp mass, the frequency, the time of coalescence, the phase, and the frequency domain, the amplitude and phase. Now what we actually detect is not the strain directly, is combined with some noise in it. So we need to see the power spectral density and recognize the noise better to see the strain better, or to understand the strain better. Now we see the power spectral density for this. This PSD or power spectral density is denoted by Sn as a function of f. Using this we can calculate the SNR, the signal to noise ratio, like this, dividing the strain in frequency with PSD integrating with the constant gives SNR square. If SNR exceeds a certain threshold, we check through the false alarm probability whether detection is of a signal or a noise mimicking a signal. We use this formula for false alarm probability, and after only that we can conclude that detection of a signal has been concluded. So the detection we get is actually of a signal, not a noise mimicking the signal. And with this signal we can now go to the simulations. This is the chirp mass, chirp signal I have taken. This is the power spectral density, and you can see here this is the most sensitive region for the PSD which we take. As you can see, the lower the value of the PSD is, the higher will be the SNR. So the more the SNR, the better detection we do. This is the chirp signal, the segmented noise data, and the PSD estimate of the average Fourier transforms. And so now we go to the injection recovery of different parameters. Here mass for different waveforms. Here we have injected mass m1 to be 35 and m2 to be 30. As you can see, this yellow band here shows the recovery, the best recovery region, with the red as the injected mass. If you notice, we are here actually seeing the summation of the two masses m1 m2. The yellow band shows the summation 35 plus 30, and so the injected parameter lies in that band. And this one here is a similar one, but here we have injected the waveform SEO BNR and recovered by IMR phenom D. Now yes, yes sir, we don't get it from the mass, we actually use a strain and find it from mass. We actually get a combined chirp mass using the from the strain, and then we see the summation. That's why we see the summation of m1 and m2 like that from the strain. And depending on the waveform, the summation will remain the same, the region will be same, and we check for which value the best match is seen. So you can see I have said waveform models here. We have used two different waveform models here. This is because we don't actually see the detected strain as it is, and even if we do, we can't actually solve it for getting the masses. For that we need to solve the Einstein equations, which is not entirely possible. So we take this waveform template, say, and then try to fit it with the noisy data or strain we get, and for that we change the amplitude and all, and with that we find the best match of the for the injected parameters. Now different waveform models like Taylor only show the in-spiral part. SEO BNR shows the in-spiral merge and ring down part, and the best one is the IMR phenom C&D for all the domains. They show the full waveform. We can see it here, like if we use and compare for different injection and recovery of using different waveform models, you can see for Taylor the recovery injection is 0.7. For IMR, if both are IMR, is 0.98, while the other two in the combinations false. Like here it is 0.696, and you can see it here, and here it's 0.668. So we almost get a perfect recovery for IMR, 0.1, this is 0.984. So matching the waveform correctly is actually important, and this is actually because we get the full waveform information in IMR, not a part of it. That's contributing to the effect of the for the best match here. As you can see, this is the waveform. So going to the real data, we are in this one. Yes. Yes, sir. It is in the log scale, sir. It is here in the log scale. The x is the log scale. The x-axis is in the log scale, and you can see it here. So like in this plot, we clearly show it is in the log scale with the plot grids and all. But here we don't show it with the grid, but this is in the log scale. The data is in log scale. Yes, I think we can use double log here. I think we can use double log here, but for that the waveform will change. Like without going like this, it will go something like this here, like that. I've not seen it yet, but I think we can use it. So going to the real data strain using here, we can see for two black holes of different masses, there are two intrinsic parameters, two component masses m1 m2, and 6 component spins for each of the binary, and we have other extensive parameters: sky location, luminosity distance, binary orientation, polarization angle, and margin time. For this study, I have considered intrinsic parameter. I have not taken extensive parameters. This is the real detector strain we are using with the RA and DSC value of 1.7, polarization angle 0.2, and F and F cross of these values. This is at LIGO Livingstone L1 detector. As you can see, the orange one is the detector projector wave we have generated using PyCBC, and the blue one is the manually generated one using this formula. It is the difference is really small considering it is 10 to the power 9 scale. So we work with this waveform here. Yes, it is 10 to the power 9 scale. Yes. Compare the projector strain, and this is the actual LIGO strain we are using, and this is the recovery data we have gotten. Here we have used grid based detection. The best match is 0.937 for, and recovered values are 35.9 and 29.23 solar masses with bias of almost 1 solar mass. Here the white cross is the best match and red is the indicator value. So now extending the study for grid with one spin parameter, spin z, you can see although we get good results, the best match is 94.4, and but the computational, it is computationally expensive now. Like for 4000 waveform templates it takes 30 minutes, so for around 9000 templates it will take in like 2 hours. It is computationally expensive, so we need a new solution. That's where particle optimization comes in. Inspired by the swarming behavior of birds going towards a target, like this you can see, we use this formula where vi is the velocity and xi is the positions for each particle, w is the inertia, c1 is the cognitive coefficient, c2 is the social coefficient. The inertia maintains the momentum of the momentum of the particle. The c1 makes for each particle reach its best match, and C2 makes it makes each particle known for the best match gotten by or attained by every particle. So analytically, say assume we have this waveform, the normal distribution, and we are bombarding like 10 particles here. If one particle reaches here, the say at the peak, all the other particles will follow it. So this is the injection for noise free data for 10 injections of masses. You can see most of the matches are 1. From this plot also you can see that for the injected parameters m1 and m2 and the bias in the masses. Now comparing with grid search, we can see PSO is way better in estimating the accuracy. There is more for PSO compared to grid. Here the blue line with the dot shows the injected mass parameters, and the orange one, the PSO, almost recovers all the masses perfectly, while the grid falters and falls behind in accuracy as well as estimating the masses. So we can see the PSO is faster computationally and has more accuracy. Now trying for 100 injections with noise, you can see these are the plots for the masses and the biases here, and you can see the biases well in this plot also. Here, as you can see, the peak this line, sir. No, sir. It will be here, sir. Yes, sir. We are actually plotting the injected mass with the recovered mass. So it is not a best fit line. If the recovery is correct, it will follow this line. Uh, no, we are plotting it like that. Here, if the recovery is correct, say if we perfectly recovered the yes, if we perfectly recovered the masses, say the best match is 1, then it will fall in the x equals to y line, this one here. Yes, sir. Yes, sir. Yes, sir. Say take this point, like if the masses is biased here, like no, yes, yes, sir. Let's say this is a true line. These are truth lines, so the particle will be here as we are plotting injected say this is the true line. This line this one is the true line here. If mass is well recovered, it will fall in this line. Otherwise, if it shows bias, it will fall here. Take this particle, this one shows the bias downwards and this one will show the bias upwards. This is because we compare the total mass sum. Like you can see here, the total recovery peaks at 0, so the error bar is less, the error in masses recovery is less, it peaks at 0. And these are the injection and recovered SNRs, injected recovered SNRs, which are plotted from PSO. Now coming to the main result of the PSO, so we are searching for this mass group of binary black holes BBH3. We have injected 500 injections. We have assumed no spin. By no spin, I mean we have assumed not taken into account all the 6 spins. Like if you see back here in this slide, no, yes, this slide, there are 6 spin components, 3 for each binaries. So we have only assumed 2. We have assumed 2, one for each in the z-axis, and we have taken the detector to be of Hanford H1 and the template waveform to be IMR phenom PV2. These are the particles. We have taken number of particles 200. The mass plots, these are the mass plots, and spin plots, spin 1z plots. As you can see, the spin is not well constrained like the masses. Although the mass shows a constrained recovery, the spin is not at all constrained. We can say how well it is recovered. This is because we have taken only 2 spin components out of the 6. Uh, Here you can see, in this plot we are plotting the chi effective. We are weighing the spins with the recovered masses and then plotting it. This shows how well the spin is constant, as you can see. So the chi effective is well constant, and this is the chop mass we have plotted, and this is how it works. This is how PSO works for the fifth injection of this sampling. As you can see, this particle which starts here gradually converges at this point, near the true value. I would like to conclude by saying how choosing the correct template has a huge impact on recovery, and why PSO is important for higher dimensions, as it lowers the computation time as well as increase the accuracy of recovery. As a part of future study, I want to study why here we got a slight bias in the recovery of the mass parameter m1. As you can see, there is no, it is not a normal distribution as it should be. Although the chop mass is constant, we got this bias may be because we have only chose a single detector instead of choosing a multiple detector system. These are my references. Thank you. This slide, sir. This one. Yes, sir. Yes, sir, I did it. I have seen it. But, yes, yes, sir. Yeah, I will do it, sir. I will do it, sir. I will do it, sir. I'm sure about these 3 that they have been published in journal. I have to check for the other 2. Yes, sir. Okay, sir. Okay, sir. Okay, sir. Yes, sir. Okay, sir. I will do it, sir. I will do it, sir. Okay. Yes. Mhm. Yes, sir. Yes, sir. I will do it, sir. Okay, sir. Uh, this one. This one. Yes. Yes, it will remain same. It will remain same. Even if the spins, if you take different spins, it will remain same. See, I'm taking 2 spins, right? Even if you take 2 or 3 spins, it will remain same, irrelevant of the axis you take. Unless you take 6 spins or more, it will get more constant. But unless you take 6 spin, the full parameter space, it will not be as constant at the masses. Hmm? This one here. Yes, yes, the spin, the chop mass will have the same unit of solar mass. See, you are taking 2 masses, right? But we don't get 2 masses in the detector. We see the sum together. So we are trying to see how the recovery works as a model, like how it works for the combined mass, the chop mass, along with it. We are getting the sum, so we are seeing combined mass. As you can see, the masses separately are not that constant like the chop mass. Similar to the spins, like compared to spins, the capacity is more constant. Yes, sir. Yes, sir. It will have the same unit. The mass. Yes. Uh, the chi effective. Yes, sir. This will have the same unit as the spin z. Yes. This one also will. Yes, sir. It will have. Uh, Yes, it will have the same unit as solar mass. With the as like the masses, like it has, it's 6 by 5 by 1 by 5. So yeah, yeah, like that. Yes, 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 yes. Yeah, yeah. Like see, for the masses, we are here using mi, but we are not actually getting mi. For the individual mass, we are getting the observation is combined, like mz, sharp mass, and mass ratio q. Like here the sharp mass, you can see, like if we here yeah, if we plot the q, this is how we are getting the truncated q value from 0 to 1 range. This one is the 1 part. These are the mass ratio distribution, and for the mz distribution, it will follow this line and get scattered here like this. This is the redshifted sharp mass distribution we can get. And yes, uh, yes, it will remain the same. Yes, you can, here we are only considering the, yeah, we are considering the combined one. Yes, yes, yeah, yes, 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 yes. It will remain same. We are not taking as whole. Yes, yeah. This one, yeah. This is the formula. Yeah. Yes. See, this is the Chapman's formula we are using. It is similar to rest mass or yes.
If anyone does not have any more questions, I think we can thank our speaker Aritra for his presentation.
Okay.